Swayam Prabha. Digital India. Educated India.
So welcome to this part of the lecture in soil technology. My name is B.S. Das. I'm from Agricultural and Food Engineering Department, Indian Institute of Technology, Kharagpur. So today we are going to talk about soil water regime. We have in the previous lectures talked about soil as a porous medium. In particular, we have talked about soil as a three-phase system, and specifically soil as a solid phase, and then the pore space, which is occupied by water and partially air, and so that makes it three different phases. So air and water, both of these phases have this capability to flow. We call them together as fluids, and specifically both water and air are complementary to each other because the pore volume in a soil is fixed, and so once a portion of that pore volume is occupied by water, the remaining ought to contain air. And so the proportion of this pore space occupied by water ought to be equal to the proportion, the volume, which is total volume of the pore space minus the volume of the air phase. So today we are going to talk about this water part of the three-phase soil system, and also this is the first of these in the series of lectures when we talk about different kind of processes that really occur in soil, and so in particular we talk about processes such as what happens to water, processes such as what happens to different kinds of nutrients, chemicals, or energy, such as the thermal regime of the soil, or the nutrient status, for example, in soil. So some of these processes are intricately related to soil water regime, and so as we have really developed an understanding about soil as a three-phase porous medium and a three-dimensional body. We are in this part of these lectures, we are going to look at mostly the soil water regime. And water regime, if you look at controls a lot of things in soil, just as I mentioned about the soil air phase and soil water phase, would really, from a volume occupation point of view, are going to be really complementary to each other. And so similarly, all kinds of processes that occur in soil in presence of water, water plays a vital role, and so it's a very, very important part of understanding soil and technologies involved in soil. And so let's get into soil water. And before I really get in, I would like to really share with you some of these very interesting numbers when it comes to water. Many of you guys perhaps know that water is a very, it's a key component of our system. Almost up to 90% of some of the organisms could have water. So water is pretty much integral part of the living system. When it comes to human being, many of you guys should know that 60% of our body weight is water. Brains, for example, 70% is water. Blood is more than 80% water. Lungs is water. It's about 90%. And so these some of these numbers are when it comes, tells us that water is a very, very important thing when it comes to living systems, higher living systems, animals and human being. And when it comes to our requirement, we are primary users of water. Almost, the World Health Organization says that we need about 30 liters of water per day, and so that's a large volume of water. We consume. Imagine that each one of us consuming something to the tune of 11 cubic meter. So a cubic meter is 1,000 liter. So 11,000 liters of water a day, water a year. Imagine with 6 billion people using that much of water, we have a large water requirement. Coming to the things that we are directly linked to it in this particular class, agricultural sector. The next important water user is the agriculture sector. Many of you guys probably do not know, the thing, the rice being your staple food. When you are eating rice, a large volume of water is needed in growing rice crop. People have estimated to the tune of about 5,000 liters of water is necessary to produce just a kilogram of rice. If you look at the water requirement of rice crop, for example, you will see that almost to the tune of 150 centimeter of water. That's about 1,500 millimeter of water is needed to just complete one life cycle of a rice crop. Something in the order of about 90 to 120 days. So 3.5 months of a rice crop would utilize almost all the water that you get in the whole year from the rainfall event. And so water, for the production of the rice, which is our staple food, is a very important component. If you look at irrigation perspective, almost 20% of our entire global cropping depends on irrigation. So an irrigated crop is more productive. You can see that the total 40% of the total food production comes from just 20% of our irrigated land. And if you look at for a second, just meeting the requirement to irrigate 20% of the world's cropland, we really utilize approximately about 70% of all the fresh water that we can withdraw, and so that's a large water utilization for the agricultural sector. A bit more in terms of sort of a resource mapping point of view. If you look at our Earth, of course, 70% of the Earth's surface is covered with water, and when you look at all the water that we have in different water bodies and the water that is there in the ice, ice caps locked. If you look at that, that's almost over a billion cubic meter of water, 1.36 billion cubic meter. That's the estimate, and all this climate change happening. Imagine that whole water, melting away would really cover this entire Earth to a height of about 3,000 meters, or 3 kilometers of water depth is going to be covering the entire globe. Fortunately, fortunately, a lot of that is locked in the ice caps. So only if you look at about 2.5% of the total water is the fresh water. Most of the water is in the ice cap. Most of ice caps. Most of the water is in the oceans. Freshwater component is very, very small, just 2.5%, and of that, that to 75% is in the frozen condition in the polar regions. Just about a quarter, 23% approx stays inside the groundwater, and some of them, rest of them, about say a quarter again, in lakes, rivers, atmosphere, moisture, the soil and the vegetation. Those are the 20, so that's about quarter of about 2.5%, of the total water that we have. So that's a pretty small, that's pretty small fraction of water, good water, or the fresh water that we have. Now, one of the interesting thing is that, first of all, we have a small amount of water, and that too, only a third of a percent is of that is renewable. That means you could replenish that. You could recover that once you utilize. That's So imagine that 100%, only 0.3%, third of a percent is replenishable, means you can really recover it in the after utilization. And so that's again a big challenge. No wonder we have almost quarter of a population, 23% of the world population, if you look at out of the 6 billion, 2 billion people, what that's about, right now, such a large fraction of people live under chronic water shortages. If you come back to the Indian scenario, for a second, if you look at like 100 years of rainfall pattern, because our most water comes from the rainfall, and if you look at from 1901 to about say 1914, and if you look at this, these are the annual rainfall that we show in the y-axis. You could see that on an average, about say 1200 millimeter of rainfall for the country. And if you look at their distribution, June, July, August, and September is the lion's share. That's the monsoon water, and so you could see that roughly about let's say about say 200 in each month. And so around 4 months, around 800 millimeter, 800 or 900 millimeter of water out of the 1200 millimeter we get during the monsoon months. So 4 months of from June, July, August, September, you see that lion's share, almost about 70% of the total rainfall of 1.2 meter we have during the monsoon months. And when it comes to this, source and the requirement gaps, it's a pretty challenging condition right now. We have almost 600 million people. That's almost half the population. Half the population face high to extreme water stress. and that's not a very useful thing. Well, if you look at little bit of distribution perspective, what happens to that total 1.2 meter of water that we get, you know, so if you look at that, we have 1.2 meter of rainfall, and that spreads over about 329 million hectares of the total area, geographical area that we have. So that's about 3.29 million kilometers square. So if you multiply that, you get around 4 million cubic meter of water. And if you look at that, half of that water enters into the soil. So through the process of infiltration, it's about 2.15 million cubic meter, and the other half essentially gets lost through the overland flow, or what we call as the runoff. Right then and there, you could see that there is a huge opportunity for us to really save that water from being run up, getting into water bodies, and perhaps eventually losing to the ocean system. Nevertheless, half the water that really infiltrates the soil, you could see that just 30% of that, about 1.2 million cubic meter, is stored in soil, in soil as soil moisture, and you could see that about 1 million cubic meter enters or gets added to the groundwater table, and out of that about 0.42 million cubic meter is usable, and specifically out of that entire 0.95 million cubic meter that enters or added to the groundwater, only we at this point leaped about 0.12 million cubic meter. Our evaporation component is again almost a third of the water, so that's about 0.7 million cubic meter. Our runoff to different kinds of water bodies, therefore, is about, as I mentioned, 1.15 cubic meters. So this evaporation and the runoff component is almost half the water that we get out of this 4 million cubic meter. And but again, from the water that gets into the different water bodies, and things like rivers and ponds and canals, all those, you could see that from the rivers alone we get about 0.27 million cubic meter. So if you look at these 0.27 million cubic meter and about 0.12 million cubic meter that and out of that 4, therefore it's about 0.4 million cubic meters. So 0.4 over 4, it's about 10% of all the water that we really get through the rainfall. We lift it and use it for our utilization. So you could see that there are opportunities, therefore, for us to be able to some way improve the use efficiency of our rainwater harvesting. Therefore, is a very important step, because we are not really utilizing the full potential of it. We are kind of just utilizing about 10% of the rainwater. So we have a huge opportunity to improve the water use efficiency in terms of how much water we can get for our use from the total rainfall. Okay. So with that sort of a number games that you see, to summarize, therefore there is a very important thing that we see that we, in one hand, we have plenty of water coming out of rainfall. We are only utilizing about, say, 10% of the water, lifting it from the reservoirs, so whether it's a groundwater or it's a open water body such as a river. And we are seeing that about only half of the water that we see get it from the rainfall is entering into the soil. So there is an opportunity to have that water, more water, enter into the soil, and then perhaps reach our groundwater systems. On the other hand, what we see is that we, almost half the population in our country alone are staying under water scarcity, extreme water scarcity condition, and this challenge is not alone specific to our country. It's a global problem. Imagine a large fraction of the global population facing these water scarcity. And so we have a big gap between what resources that we have and how much we utilize, and how much shortfall that we suffer from in terms of water scarcity. So as you can see, that soil obviously plays an important role. And if you remember, we talked about in a hectare of land, for instance, if you are looking at a density of about 1.5 grams per cubic centimeter, or if you're looking at a porosity of the 50% of the total volume, we calculated something in the order of about 1,000 cubic meter, or about a million liters of water can be stored if we really have it just top 20 centimeter of the soil in a hectare of land. So 100 meter by 100 meter area is saturated, and so there is this opportunity to trap the water in soil, to store it, and perhaps use it in a more efficient manner. And so that calls for a greater understanding of our how water and soil are linked. And you know what, as you really try to utilize your knowledge of agricultural science or agricultural engineering, one of the key resource management issue is the water management, and for the agricultural sector. And so your understanding about how water behaves in soil and what happens to water is a really key element. So when it comes to water, if you ask me, I look at from two perspectives. The first one is, when we want to really manage it, the first thing, it's kind of almost like a banking problem. How much money do you have, and how much you really spend it. So in a similar fashion, from a mass balance point of view, you really ask this question: how much water is present in a soil at a given point of time, or in some specific location? That's the first information that I would like to really have. The other information I would like to have, which is of course related to the first one, is that, okay, if I have some X amount of water in the soil, how long that water is going to stay there? Because the idea is, soil, water, and air, they are going to occupy a fixed volume, right? So therefore, anytime water is leaving that pore space, air is going to occupy. Obviously, my total amount of water would be left out, would be less. So these two important components, we need to understand very, very clearly. Okay. So let's look at the first key question: how much water is present in the soil? Well, how can we do that? Perhaps go out there. You need to measure how much water is present, or some kind of a you go through some kind of an estimation, indirect estimation process, instead of directly able to measure it, right? And so but in both the cases, what you really have to sort of have some kind of way of describing that soil water. And here is how you could, very simple, you could really describe what is water content in soil. In a very simple term, you could probably describe it in terms of a mass basis, as water content equals to the amount of water present per unit amount of soil. And when it comes to uh, similarly, you want to talk about how long that water will stay in that soil. You would say, well, it depends on the rate at which that water is get lost. And you could probably write an equation similar to the water content like this. Rate of water loss would be how much water is present at some time t1, and what is the amount of water left out after some time. And so you go to a second instant in time t2, and then so t2 minus t1 gives you that duration. So wetness at time t1 and wetness at time t2, that difference gives you the change in the storage. And so change in the storage over the change in some kind of a duration tells you at what rate water is either added to the soil or is lost from the soil, right? So these are the two fundamental questions that you want to answer. So let's kind of go a bit more details, and so find out how we can deal with this, how much water is present in soil. So as we mentioned earlier, the water content, you could really describe it in terms of the amount of water per unit amount of soil. And either you could really say that in terms of some kind of this mass of water over this mass of soil, which you could say that that's a sort of a mass basis or gravimetric water content. You could also describe the amount of water present in terms of volumetric water content, right? Theta V. Theta is I use for water content, and the subscript G for gravimetric, and V for volumetric. And so you can see that theta G, or the gravimetric water content, is expressed in terms of the ratio between the mass of water over mass of soil. And again, this mass of soil ought to be again the oven dry mass of soil, because you remember in our mass volume calculations we have always taken the dry mass of the soil. Oven dry mass, that is, the soil is dried at 105 degrees centigrade for a period of 24 hours. So mass of water divided by oven dry mass of soil is the gravimetric water content, and volume of water over the total volume of soil is the volumetric water content. And you could see that we could multiply this theta G by a ratio between the bulk density of soil and the density of water. So that really gives you a relationship between the volumetric water content and gravimetric water content. And so you could assume that the density of water to be unity, and so basically the product of theta G to the bulk density gives you the volumetric water content. So if you look at this volume of water per unit volume of total volume of soil. So this tells you what volume fraction of the total volume of soil is occupied by water, not the volume fraction of the total pore space. It's the total volume. Okay, so let's kind of do some simple calculations to kind of have a feel for what is or how much this water content and what it means in terms of actual soil measurements. So here is a simple problem. We have, let's say, a moist soil of about 250 grams, and so we would oven dry it, so at 105 degrees centigrade for 24 hours. And let's say we got for this particular sample, the oven dry weight was is 200 grams. We measured this bulk density to be 1.4 grams per centimeter cube. And so if you want to estimate the gravimetric water content and volumetric water content, these expressions that we show for theta g and theta v is going to come very handy to estimate this. So we can see that total mass of water divided by the mass of soil. And so we have a moist mass, which is 250 grams. We have a dry mass, MS, which is 200 grams, and we subtract those, and we get the mass of water. Divide that by 200 grams, and that's the MS, oven dry mass. And so we have a gravimetric water content in terms of mass of water per unit dry mass of soil. And then sometimes you really get sometimes you really make a mistake. Instead of dividing this mass of water with mass of oven dry soil, you sometimes divide it with moist soil, and that's we don't want to do, because of changing water content, the moist for the same soil, the moist weight of the soil will keep changing. And so we want a more intrinsic estimate for the water content, so we should not change with we are trying to estimate the water content, and if that changes with the amount of water being present, and that's not going to be very comparable quantity. And so we want to always express gravimetric water content in terms of oven dry mass basis, not the moist mass of soil. So MW over MS. And so similarly, we could get this theta g, we multiply with the ratio of the bulk density to density of water. We see that theta v is equal to 0.35. Next part of the some of the terminologies also that we sometimes used is that what happens what happens if all the pore space is filled with water. As you know that the porosity is the ratio between is defined a ratio between the volume of pore to the total volume of soil. We know that porosity also is equal to 1 minus the ratio of the bulk density to particle density. Particle density remains constant at 2.65 gram per centimeter cube. And so water content at saturation, when all the pore space is filled with water, and so the volume of water there is going to be the total volume of the pore space. So therefore theta saturation, theta s, and again these are volumetric water content, is going to become equal to the porosity of the soil. Sometimes we also talk about just like one extreme is the complete saturation. We also talk about something called a residual water content. And residual water content is such in sometimes we use it as a concept to describe the water which you cannot easily remove it, so which is left out even you dry it quite a bit, and not maybe oven dry basis, but you can think about some kind of an arbitrary wetness which you cannot dry it, which cannot remove it easily. So that is something like a irreducible water or residual water. And so what you can think about some kind of an effective wetness, which would be therefore would be the current wetness, and again, you can see that this theta is now I'm going to use mostly the volumetric water content, and so theta minus theta r tells you the some kind of a measure of effective wetness. And so again, you could really, similar to effective wetness, you can think about a relative saturation. So that becomes the ratio between the effective wetness at a given level of wetness and divided by the effective water content at saturation. So basically SE equals to theta minus theta r divided by theta S minus theta r. And so let's do a simple calculation again for the same problem that we had where our volumetric water content was about 0.35. Let's see if our theta r or residual water content is 0.05, then what happens to our relative saturation? As I mentioned earlier, our theta s is basically 1 over minus the bulk density divided by particle density. So this is the total porosity for this soil is about 0.47, and so theta s is going to be equal to 0.47, and so therefore now our relative saturation is going to be equal to 0.71, and so when you look at this volumetric water content versus effective water content versus relative saturation, what is happening is that in case of soil, as the density changes, the porosity keeps on changing, and so therefore from one soil to the other, you will see that the total porosity changing, you are going to see that the saturated water contents are going to be different. Theta s going to be different. So if you are to really compare two soil condition, wetness of the two soil conditions, you will see that their capacities are different. The capacity to hold water is different because theta s is different because of the change in densities. And so therefore, to really to help us tackle that the extreme value of the soil wetness, which is theta s, what we do is sort of normalize it with the porosity. So theta, you can think about a normalized water content to be theta over theta s, or the theta over porosity, and then the lower side of the wetness, when we cannot dry the soil beyond certain limit, for example. So therefore we sort of say that, wow, that is the residual water content. So think about a water content starting from 0 to some kind of a theta s, and so what you have is sort of an effective and what, so here is some kind of a theta r. Let's see if I can use my mouse for a second to write that. Okay, here. So what we have is a theta r here. Okay, so the effective wetness is essentially this from theta r to theta s. Okay, and so therefore our SE is equal to our theta minus theta r divided by theta s minus theta r. Okay, so you can see that the moment this theta is equal to theta r, so SC equal to 0, and when theta is equal to theta s, that means the soil is fully saturated, this SC is equal to 1. So what we get is that AC has a range from 0 to 1 for all soil. My mouse is not working very well. So from all soil, the the AC go range from 0 to 1. Okay, and so these kind of sort of numbers for soil wetness now allows us to really compare two soils. All soils would have relative saturation ranging from 0 to 1. So you could really compare two soils in terms of their relative wetness, relative saturation. A few other quantities come very handy when we need to describe the soil wetness. One of them is the depth of water in soil. As you can imagine, many times we talk about, what is the depth of rainfall that we have. We say that it's about 1200 millimeter of rainfall. So that 1200 millimeter of rainfall is really spread over this entire land surface, and so that's how you have this total volume of water present on the surface of the soil, right? And so just like rainfall in terms of kind of a depth unit, depth of water, sometimes we also talk about depth of water in soil. So something like an equivalent depth of water. And so the way we describe it is that, imagine this, when we have depth, if we want to really know what is the what is the volumetric water content. Volumetric water content is what? Volume of the total volume of water divided by the total volume of soil, right? The total volume of soil is going to be what? The depth of soil and the area of the soil. So A times ds is our total volume of soil. So if we multiply that with theta v, what we get, so this numerator up here is actually the total volume of water present in soil, right? And so if we divide that with A, the cross-sectional area, which think about that water is pretty much spread over that area, so what we have is a sort of equivalent depth of water standing in that on that surface, right? So therefore you can see that this A cancels out. So the product of this volumetric water content to the depth of soil is basically the depth of water, right? So just give an example, estimate the depth of water in the same example that we had in the top 20 centimeter soil. If this sample was taken from the same soil that we have, example that we have, right? So what do we need to do here? We need to estimate the, so that's the second part of it too. Estimate the volume of water needed to saturate this soil. So we have an existing wetness of 0.35 and we have this total area of 1 hectare. Depth of soil is 20 centimeter, and we want to know how much total water is present and how much more water we need to really fully saturate that soil, right? That's the question. So the answer is very simple. If you can find out what is the depth of water by simply multiplying the depth of soil to the volumetric water content. Our volumetric water content was 0.35. We multiply this 20 centimeter. That's our depth of soil. So we have about 7 centimeter of water present in that soil, right? And similarly, if we look at what is the amount of the depth of water in that soil when if all the pore space is filled up with water. So we know that when all the pore space is filled up with water, our volumetric water content is going to be equal to the porosity, and we call it the saturated water content. So our saturated water content we calculated in previous slides to be 0.47. We multiply 20, so you have 9.4 centimeter of water, right? So we have 7 centimeter of the water in that soil. If we fully saturate it, the total amount is going to be 9.4, and so therefore we need about 2.4 centimeter, 9.4 minus 7, so 2.4 centimeter of water to fully saturate this soil, right? And how much is going to be that in terms of the volume? We have this 2.4 centimeter, which is about 0.024 meter. We have the total area to be 100 meter by 100 meter, and so you multiply that, you have total 240 cubic meter of the water which is needed to saturate the soil, right? Well, we also talked about this, the total pore volume being very fixed, the amount of the water volume wetness and the porosity or air-filled porosity, is going to be complementary. So similar to the volumetric water content, which is defined as what? The volume of water divided by the total volume of the soil, or the bulk volume of the soil. You can also describe the aeration porosity to be the volume of air present and divided by the volume of the soil. And so, you can see that the aeration porosity therefore is going to be simply equal to the porosity minus the volumetric water content, right? Because porosity is the total volume of pore space divided by the total volume of soil, and you subtract out the total volume of water, and you are left with volumetric water content of air-filled volumetric content of air, so air-filled porosity. So for this case, what is going to be the air-filled porosity or aeration porosity? So we know that our volumetric water content was 0.35, our porosity or is equal to 0.47. So about 0.12 would be the aeration porosity, and again, multiply that 20, you get total volume of with the area, total volume of air present in that soil, so in 1 hectare of land. In addition to these constants about volumetric or gravimetric water contents and relative saturation and depth of water, we also sometimes talk about this available water content. And when it says the available, they are actually the plant available water content, right? And so the way we define them is that the water held between the field capacity of soil and a permanent wilting point is the available, and this is actually available constants available to the plant. And so available water capacity is the theta FC, or field capacity, minus theta wilting point, theta WP. And let's describe these two quantities first. What is the field capacity? Field capacity is kind of a starting point in the soil. So what we say is that, if you saturate the soil, water which is present in the very large pores, gravity is going to pull them down, right? And so all the large pores or macropores, you can imagine, where water cannot stay there, it would immediately be drained because of the gravity. When they are empty, whatever is the wetness, whatever is the amount of water left out, if you express that in volumetric terms, that would be called the water content and field capacity. And typically people, as a thumb rule, what they do is they saturate a soil and allow that water to drain for 48 hours, so 2 days. And so essentially it is assumed that in that 2 days period, or 48 hour period, all the large pores, all the macropores are going to be drained or would become empty, because gravity would really pull that water from the large pores, not from the capillary pores, not from the small size pores, because small size pores will be able to retain that water, and we talk about that water retention later on. And so when water basically is drained out from the saturated soil, all the gravity drainage stops. Whatever amount of water left out, we call it a water content at field capacity. And traditionally, if you look at from from an energy perspective, and again we'll talk about this in more details when we talk about water retention characteristic. If you look at at what energy features with which this water is held by the soil is almost in the order of about third of a bar for most of the medium and the fine textured soil, to about tenth of a bar for the light textured soil, because the light textured soils, you will have water being drained out faster, and so we talk about 1/10 of a bar is a little larger energy than third of a bar in terms of, well, smaller amount of, larger in terms of number but smaller in quantity. Okay, and so basically what happens is these water which is present in the large pores, they don't get used by the plants, because by the time plants come and try to absorb them, they are basically removed because of the gravity drainage. So that's why that part of the water is not utilizable. So you can think about our water line again. Somewhere we have this theta s. Somewhere up here is our theta fc, means, so this water is not available at all, and so somewhere here again there will be a theta field, theta wilting point, and basically this difference here, this is the plant available water, and this side is not available, this side is not available. Let us define the wilting point in a second, and this will be clear. So here what the way we define the wilting point, again a static soil wetness value, is that water content of the soil wetness stage of a soil when any further reduction in the drying would really cause that plant to completely wilt. And so basically what happens is there is so little water present in soil at wilting point, is that plant roots become unable to absorb that water. So therefore, as the water content in the plant cells should decrease, each cell won't be in a position to maintain its turgidity. As a result of it, this plant shows that characteristic wilting symptoms, kind of fall, drool down kind of things. And so these sort of soil wetness is called the soil at wilting point. And if you look at what energy with which this water is held, that's a pretty large number. Water at that point is pretty much as smears, as kind of in the adsorbed surfaces on the solid phase, and not much free water, and the energy with which that water is held are in the order of about 15 bar. So soil wetness, we call it a 15 bar soil water potential, and again we talk about soil water potential in more details. And so we still have some water at wilting point, but plants cannot utilize it, and so therefore there is insufficient supply. Plants fail to really maintain the turgidity of the cells, and so therefore show the wilting. And so these two conditions, from wilting point to field capacity, that is called the plant available water. Well, so let's do a little bit of calculation. We have a soil mass of 85 grams, a mass wilting point, soil mass at field capacity is 85 grams, soil mass at wilting point is 71 grams, and air dry mass is 64 grams, oven dry mass is 58 grams. Find out this water content and field capacity, wilting point and plant available water content. Here are the calculations. Water at field capacity, therefore, is going to be, we have to subtract out 58 from 85. That's the dry mass of the soil. from the weight of the soil at field capacity, and divide that with 58, so that you get about 47%, and this of course is the gravimetric water content, because we are kind of describing the water content in terms of mass of oven dry mass of soil. So it's a mass of water divided by mass of soil. Similarly, for the wilting point, you could see that 71 minus 58 is 22, and so this plant available water, which is the water content at field capacity minus the wilting point, therefore ought to be about 25%. So this is the available water. Similar to really these concepts are utilized nicely in case of soil to really look at tackle this heterogeneity. You can think about the total available water capacity in the root zone, and the root zone you could really divide it into several layers, and this available water capacity, you multiply the depth of the root zone similar to the depth of water, you have a total available water in terms of depth. And so you can, if you have multiple layers from layer 1 to layer n, you could really estimate the depth of water in each layer and sum it up, and so you will have this total available water from the profile for plants to absorb, right? A couple of other definitions that you really come across, something called the fraction of available water depleted. Think about if you have a water soil wetness, somewhere between theta fc and theta wilting point, and so think about, you have this again this water line up here, this theta s here, and somewhere here theta fc, and somewhere here it's your theta wilting point, and we are talking about a wetness, let's say at this stage, then your fraction of available water depleted is basically this water, this part of the available. So the total available water is from theta fc to theta wilting point to theta fc. So you can think about this fd and the fraction available water remaining as the amount of water between this field capacity to whatever you are having right now, and versus, so the available remaining becomes this component of it, right? And so you could essentially this is done because as you kind of try to manage the soil water regime for having better crop growth. Yes, all the water between this wilting point to this field capacity is available, but you don't want to dry the soil all the way up to wilting point. The plants are going to really suffer from water stress, and so always there is some kind of an optimum soil wetness between this theta wilting point and theta fc, and so you need to really sort of keep track of, okay, how much water, what fraction of the available water is already deeply I have lost, and how much is I'm having it right now, so that the plants can really absorb it, and that if that amount is low, then there's a trouble. Then you need to really go out there, do the irrigation. Okay, so some of these quantities are very, very helpful in terms of making this recommendation of how much water to apply. And so all these quantities that I discussed from different ways, you could describe the soil wetness from gravimetric water content to volumetric water content, and through this effective wetness to saturate to relative saturation. And then we talked about the depth of water, we talked about the plant available water. So each of these quantities really tell us at a snapshot of a time at a particular location how much water is present. So the next big thing that really comes, that well, how do we really measure this amount of water which is present, right? And so essentially, if you sort of look at, we only dealt with the first case, first key question, that well, how much water is present. Well, that, as I mentioned earlier, that is linked to how much water may be lost over time. So here's a simple calculation that is there for you to really have a feel for it. Think about, you have a soil profile. Here we describe in terms of volumetric water content. So here's a 30 centimeter deep profile here. We have this the first, second, and third layer, and we, let's say we went there, measured the wetness, from this point up here, and there is another point up here, and another point, and we have done this soil wetness profile, and so let's say we today, and so tomorrow when we go out there, and then we measure the water content again here in this layer, and in this layer, and this layer, and sort of find out what is the water content profile here. So all that water basically gets lost over a 24-hour period, and so you can think about, as a sort of a mass balance approach, how much water, what is the depth of water left out in that first layer and second layer and third layer after 24 hours time. And so you can estimate a total water depth of water in that profile, and today, and you, as the water drains out, tomorrow when you find that 4.16 centimeter of water is left out, so that leaves us that 2.04 centimeter of water ought to have really lost from this layer, either through downward flow or through some kind of a evaporation process, right? And so what we need to really therefore look at, okay, instantaneous snapshot measure of soil wetness is one thing, but as we know that soil would keep on drying because of evaporation, or water is moving out because of the percolation process, and over time this static values are going to really change. So therefore we need to really know how this soil wetness is going to really change with time, and so to be able to do that, we need to really now have a specific approach to be able to either directly measure them, or to be able to estimate them, right? So with that, in the next class, we will get into how to measure soil wetness, and then, we sort of move into how we can measure the, how we can estimate the soil wetness, so from a kind of a process perspective, right? Okay, thank you so much.